Hello viewers, welcome back to this channel. So in this video, you're going to be handling the second part of group 4 elements. So this video is presented to you by Yusuf, and your advice share the video to your friends so that you can all benefit as a group. Proceeding, we are going to be proceeding with compounds of group 4 elements. As the first video, we are covering elements for group 4 elements, all the reactions and properties for the elements under group 4. So here we are going to be specifically looking at the compounds together with their properties and their preparation of group 4 elements. So in the first video, we said that group 4 elements exhibit two oxidation states, and that is the +2 and then the +4 oxidation states. And that means that the compounds that they form are going to be in these two oxidation states. If it's an oxide, it's either going to be a +2 oxide or a +4 oxide. And a +2 oxide is called a monoxide, and then a +4 oxide is going to be called a dioxide. So we are saying that compounds in the +2 oxidation states are going to be formed when two electrons that are present in the p sub energy level or subshell have participated in bonding, and then the +4 is going to be formed when the 4 electrons that are present in both the s and the p subshells have participated in bonding. But you're saying that the stability of the +2 oxidation state is going to be increasing down the group. Just like in the first video, you're going to be seeing that only lead is going to be forming compounds in the +2 oxidation states. Others have their stable compounds formed under the +4 oxidation states. And you're saying that the reason for that is due to what you call inert pair effect. So you put here T. And you're saying that the common compounds are going to be discussed below. So let's start with the oxides, and you're going to be saying group 4 elements form monoxides, in which the elements have an oxidation state of +2, just like I recently explained. And the dioxides, that means that the oxidation state present in that is going to be +4. Now we are saying that here, the ability to form stable dioxides is going to be decreasing down the group, whereas the ability to form stable monoxides is going to be increasing down the group. That's why lead forms lead oxide, and the others are going to be forming dioxides or +4 oxides. Reason being, due to inert pair effect, and also the stability of the +2 increases down the group, and the stability of the +4 oxidation state decreases down the group. So looking at the preparation of the monoxides, we are saying that carbon monoxide is going to be prepared by simply passing carbon dioxide over rated carbon, and we are going to be looking at this more under extraction of copper or extraction of iron. So you're saying that you can prepare carbon monoxide by simply getting its dioxide, and then you pass it over heated carbon in absence of oxygen. So the carbon reduces, what's the carbon is going to do? Carbon reduces carbon dioxide and introduces it to carbon monoxide. We are saying reducing because carbon here is in +4 oxidation state, and carbon here is going to be in +2 oxidation state. So such a reaction is being called a reduction reaction. So carbon reacts with carbon dioxide to give us carbon monoxide, and it's a reduction reaction. We can proceed by saying it can also be prepared by reduction of carbon dioxide using coke. So you get carbon dioxide, and then you use coke or burnt carbon in absence of oxygen to get carbon monoxide. And you're saying that you're going to prepare silicon monoxide in the same way. We get dioxide and then react it with a silicon or its element itself when it is hot. That means that strong heating is required. So you get in silicon monoxide, you get silicon dioxide, and then you heat it with silicon so that you can get the monoxide. Now note here, as you're looking at this, you cannot get a monoxide by heating an element with oxygen. I say that the first 4 elements except lead are going to form dioxides because for them, they have the +4 oxidation state being stable. So direct heating of the element with oxygen is always going to give you dioxides. The only way you can prepare monoxides is by getting an element and then react it with the dioxide. And that element, what it will do, it's going to reduce the dioxide to a monoxide, and the monoxide is going to be in the +2 oxidation state. So silicon dioxide reacts with silicon to form silicon dioxide. And then you can be saying that germanium monoxide can be prepared by the following reactions. First of all, you can prepare germanium dioxide or germanium monoxide by heating germanium dioxide together with germanium, just like we said for other elements. Or you can simply get germanium 2 chloride and then you hydrize it with water so that you can get germanium 2 oxide or germanium monoxide. And whenever you hydrize the chloride, this is very, very important. Whenever you hydrize the chloride, you are always going to get white fuming fumes, which are for hydrogen chloride. So notice that because these questions are very common everywhere, whenever hydrates are or chlorides are hydrated or are hydrized, we get white fumes of hydrogen chloride gas. So whenever I ask for an observation, always don't miss out that. So you're going to be saying that tin monoxide is mostly easily prepared by heating tin oxalate in absence of air. And what you do, we get tin oxalate. This is an oxalate ion. So when you heat them, always when you heat oxalate, you get two components. You get both carbon monoxide and you also get carbon dioxide. And then the remaining element is going to be tin 2 oxide or tin monoxide. So lead oxide is going to be prepared. First of all, you can prepare lead 2 oxide by direct heating of lead together with oxygen to get lead oxide. Or you can prepare lead oxide from its hydroxide, nitrate, or carbonate. When you heat lead carbonate, you are going to get lead oxide together with carbon dioxide. And when you heat nitrate, you are going to get an oxide, nitrogen dioxide, and oxygen, just like we looked at this reaction at O level. And when you heat the hydroxide, you will be getting a monoxide together with steam, because we are saying steam, not water, because heating is involved. Any reaction where heating is involved, there's no way we can have water as a liquid. It's always going to be in terms of steam. Now looking at the structure of the monoxides, we are going to be saying that this is going to be the oxide and the type of bonding it exhibits together with the structure. Now structures are very important when it comes to explaining melting points, melting or boiling points. And also the bonding is also necessary when you go to mixed questions that require explanations. Because you have to know the characteristics of covalent compounds and you have to know characteristics of ionic compounds. So we are going to be saying, but notice that this one, that the monoxides of group 4 elements, carbon monoxide is going to be covalent. That's the type of bonding it's going to have. And then silicon monoxide is going to be covalent too. The type of structure these two have is going to be simple molecular structures. I say that this table is very important because it's going to summarize a lot for you. And then germanium oxide together with tin oxide, they have ionic bonding and they are all having giant ionic structures together with lead to oxides. Now let's look at the stability of the monoxides. Now usually we look at the stability of the monoxides by considering the stability of the oxidation state of either +2 or +4 under group 4 elements. So we're going to be saying that the stability of the monoxides of group 4 elements increases from carbon monoxide to lead monoxide, and the reason for that is because due to increasing stability of the +2 oxidation state down the group. And we are saying that carbon monoxide is very unstable. And since it's very unstable, that means that it's going to be readily oxidized by oxygen in air at room temperature to form carbon dioxide, because that's the oxidation state in which carbon is most stable in. So carbon monoxide readily reacts with oxygen present in air even at room temperature to form carbon dioxide gas. Now we are saying that here, the carbon monoxide is also a reducing agent, and we are going to be looking at this more often under extraction. So it's a reducing agent in that it can reduce hot or heated oxides of copper, zinc, and lead together with iron, as all elements that are below it in the reactivity series, and also itself is oxidized to carbon dioxide after reducing. So when you react copper to oxide together with carbon monoxide picks away the oxygen so that the carbon monoxide after reducing, it becomes carbon dioxide. And the metal remains as an element, which is copper element or copper metal. So zinc oxide donates this oxygen to carbon monoxide to give us zinc solid together with carbon dioxide gas. And then lead oxide donates this oxygen to carbon monoxide to give us carbon dioxide gas together with lead. And then iron trioxide donates the oxygen to carbon monoxide to give us the iron solid together with carbon dioxide. So those are called reducing properties. So anyway, you see reacting carbon monoxide gas with an oxide, just know that you are going to get an element and the carbon monoxide gas is going to be oxidized to its most stable oxide, which is going to be the +4 oxide or the dioxide. Now proceeding, we are going to be saying that since carbon monoxide is a strong reducing agent, it is also going to be used in extraction of less reactive metals like iron and zinc. And I say that we shall look more in details about these under transition elements. So I'm also saying that silicon monoxide is also unstable. Remember that I told you +4 is stable in 4 elements of group 4, and that is carbon, silicon, germanium, and tin. So silicon monoxide is also unstable, therefore it undergoes disproportionation. And as I explained in the previous video, a disproportionation reaction is where the same species undergoes both oxidation and reaction simultaneously. So disproportionation at room temperature to form its most stable product or compound, which is silicon 4 oxide together with silicon. And the explanation of disproportionation is silicon here is in monoxide state. That means that it's in the +2 oxidation state, but it has formed the product which is in the +4 oxidation state. If you calculate for oxidation state in this compound, you find that the oxidation state here is going to be +4 because this is a dioxide. And also here the oxidation state of silicon is 0. So the reason why we call it a disproportionation reaction is because from +2 we went to +4, that is increase, or that is oxidation. And also from +2 we went to 0, that's reduction. So we call such reactions disproportionation reaction, whereby the same species, which is silicon, undergoes both oxidation and reduction. So going to germanium monoxide, we're going to say that germanium oxide being unstable, it's also reoxidized when heated in air to form germanium 4 oxide. So germanium 2 monoxide or germanium 2 oxide reacts with dry oxygen to give us germanium 4 oxide. Now, we also say that it also can undergo disproportionation, just like silicon, when heated in absence of air to form germanium 4 oxide, which is the most stable oxide it forms. So germanium 2 oxide undergoes disproportionation, just like silicon, to give us germanium 4 oxide and germanium solid. So from a monoxide, we form a dioxide together with an element or a metal. Now we are seeing that tin oxide oxidizes rapidly if exposed to air at room temperature, also to form its most stable oxidation state, which is tin 4 oxide. So when you get tin and then react it with oxygen at room temperature, the moment you expose it to the atmosphere, it reacts with the air in the atmosphere to give us tin 4 oxide. Now we are also saying that lead oxide is stable at room temperature, but when it is heated very strongly in air or in dry oxygen, it is going to be oxidized to red lead. And red lead is the same as trilead tetraoxide. So when you react oxygen or a monoxide or lead oxide with dry oxygen, when you have heated it properly, it's going to be oxidized to red lead. And red lead is the same as trilead tetraoxide. So you have to know that. And they say that this one is used in preparation of lead 4 oxide when you react it with concentrated nitric acid. So always take a note of that. Now going to the chemical properties, going to the chemical properties of the monoxides, we are going to be saying that carbon monoxide is slightly acidic. Reacting it with hot concentrated sodium hydroxide solution is going to give us sodium ethanoate. So and the reaction for that, since it's acidic, it can easily react with a base. But if it was basic, it cannot react with a base. And that's the reason why group 2 elements do not react with sodium hydroxide, because most of the group 2 elements, they are acidic in nature. So they are basic in nature. So a base cannot react with a base. That's why group 4 elements do not react with sodium hydroxide. But carbon monoxide is slightly acidic. So when you react carbon monoxide together with sodium hydroxide, you always form sodium methanoate, which is present in aqueous. So you're also saying that silicon monoxide is a neutral oxide. That means that it cannot undergo the reaction with sodium hydroxide. And you're saying that germanium oxide and then tin 2 oxide and lead 2 oxide are all amphoteric in nature. Therefore, becoming more basic moving down the group, although they don't lose their acidic character completely. They react with acids to form salts and water, just like we saw in group 2, any element or any oxide, because the monoxides here, I'm comparing them to group 2 because they are both in the plus 2 oxidation state. So that means that any reaction that is undergone by group 2 elements, though group 2 elements are not amphoteric like these ones, can be undergone by these ones in the same way. So these reactions with acids under the plus 2 oxidation states are going to remain the same. So if you have tin oxide, you react it with an acid, you form a tin 2 salt or tin 2 ion in aqueous together with water, and the same applies to lead, forming lead 2 ions and then water. We also see that they are going to react with alkalis since they are slightly acidic. They react with alkalis such as sodium or potassium hydroxide. We use these ones as standard alkalis in the laboratory, such as sodium or potassium hydroxide solution to form complexes, and the complex for germanium is going to be germanate. Complex for tin is called stannate, and then complex for lead is called a pyrambate, and the general equation is going to be as follows. So having the monoxide reacting it with the sodium hydroxide or potassium hydroxide, we use the ionic equations basically because we just want ions. So this is going to be the hydroxide. And when you're writing ionic equations, always compounds that are in solid states, you leave them, you don't ionize them. So you get your complexes in this form. And there are other alternatives of complexes, like we are going to be looking at as I gave them, because some of you are not used to complexes that are in this form, and you are sorted out. So reacting the hydroxide or the monoxide together with the hydroxide, it's going to be in presence of water to get a complex of this form. So for example, if you're having germanium oxide reacting it with sodium hydroxide, you're going to get germanate together with water. But the alternative way of writing germanate can be written as this. And this is the formula that you're used to from your O level or complex. You either write it in this form or you write it in this form. Together with the tin, you are going to form stannate. Stannate can either be in this form or you can write it in this form. And I say that you have to know how to balance reactions of each of either the element or the compound of the element with alkalis. I explained a step-by-step procedure on how to do that. So make sure that you are very good at balancing equations. Don't just cram the coefficients, but put in the work and invest in the work of understanding how to balance those equations. So reacting lead oxide with lead monoxide together with sodium hydroxide, you're going to be getting this complex. Or you can go with this alternative path. This is the product you're going to be getting. Now looking at the preparations or the preparations of the dioxides of group 4 elements, we are going to be saying that carbon dioxide is going to be made by action of a dilute mineral acid on a carbonate. For example, if you have dilute sulfuric acid and calcium carbonate, this is an exclusion. If you have dilute sulfuric acid and calcium carbonate, they may not be used in this case because we are going to be forming an insoluble calcium sulfate salt, which prevents further reaction. When you're looking at group 2 elements, we told you that solubility of the sulfates decreases down the group. So that means that if you're having those group 2 elements and then you're reacting them with concentrated or dilute sulfuric acid, such reactions cannot proceed due to formation of sparingly soluble salt. And that sparingly soluble salt is one that causes the reaction and prevents it from further taking place. So you're saying that, by heating carbon strongly in excess air. So those are some of the ways you can prepare carbon dioxide gas. And also heating most of the carbonates except group 1 carbonates, because we say that group 1 metal carbonates do not undergo decomposition. So when you're having a carbonate, you react it with any acid. For example, lead 2 carbonate react it with concentrated hydrochloric acid. you are going to get carbon dioxide gas together with water, and you also get the salt, but we excluded the salt. Or you can get coke and directly heat it with dry oxygen, so that you can get your carbon dioxide. Together we can get any carbonate and we heat it for as long as it's not a metal 1 carbonate, because group 1 metal carbonates do not undergo decomposition, but others undergo decomposition. For example, calcium carbonate can be heated to get an oxide together with carbon dioxide gas. So you're saying that silicon dioxide is going to be made straight away by strongly heating silicon in air. And for every reaction that you make, especially when you're answering your papers, you make sure that the condition is properly presented together with the product that you're forming. So here, when you want to write out this reaction, you say that heated silicon reacts with dry oxygen to give us silicon dioxide, or to form silicon dioxide. And then you give an equation for it, which is properly balanced. So when you heat silicon together and you heat it in dry oxygen gas, you're going to be forming silicon dioxide. And you're saying that germanium dioxide is going to be made by any of the following methods, and you're given 3 alternatives. So first is going to be heating the element strongly in air. So when you heat germanium strongly in oxygen, you're going to be getting germanium 4 oxide. And also when you hydrize germanium 4 chloride, or when you hydrize germanium 4 chloride, with water, you're going to be getting germanium 4 oxide. Now this is very important, because all tetrachlorides, all chlorides of group 4 elements that are in the plus 4 oxidation state, once we hydrize them, we get a dioxide and hydrogen chloride gas. I remember telling you that whenever you're hydrizing any chloride, you have to get white fumes of hydrogen chloride gas. And the same thing here. But here, since these chlorides are going to be in the plus 4 oxidation state, what we get is going to be a plus 4 oxide. So once you are hydrating germanium 4 chloride with water, you'll be getting germanium 4 oxide together with hydrogen chloride fumes. Now you can either represent these ones as fumes, or you can represent them in aqueous, because we take the assumption that this water is going to dissolve the hydrogen chloride fumes to get hydrogen chloride, or to get aqueous hydrogen chloride. But in actual sense, it can be gases, because it's always fumes that come out. So you can also prepare germanium 4 oxide together by heating germanium, or by reacting germanium with concentrated nitric acid. So when you get germanium, you react it with hot concentrated nitric acid. This is an oxidation reaction. I told you whenever you see two products and two reactants and 3 products, that's always an oxidation reaction, especially with concentrated acids, and you have to be very good at redox reactions. You write the equation for nitric acid being reduced, and also you write an equation for germanium being oxidized to germanium oxide, and then you combine those 2 equations by eliminating electrons, so that you can see how equations of concentrated acids can easily be balanced. Don't just master or cram coefficients. So reacting germanium with concentrated nitric acid, you'll be getting germanium 4 oxide together with nitrogen dioxide and water. So proceeding, we are going to be saying that tin dioxide can be made by any of the following methods. So one of the first method, you can heat tin strongly in air. So when you heat tin in oxygen, you're going to be getting tin oxide. And the reason for that, I told you that the first 4 elements, we're having 5 elements under group 4, but the first 4 elements are stable in the plus 4 oxidation state. It's only lead that is present in the plus 2 oxidation state. And now heating tin with concentrated nitric acid, you are going to get tin, you heat it with concentrated nitric acid, and this is a redox reaction. Still, what concentrated nitric acid is going to do is going to oxidize this tin and to form tin oxide. And after forming tin oxide, you're going to be getting nitrogen dioxide. The acid is reduced to nitrogen dioxide together with water. Now you can prepare lead dioxide. Like I said, we only prepare lead 2 oxide or lead 4 oxide by reacting red lead together with either concentrated or dilute nitric acid, but most of the times we use concentrated nitric acid. So this is the equation. When you react red lead or tri-lead tetroxide together with nitric acid, which is either concentrated or dilute, you're going to get lead 4 oxide. We cannot prepare lead 4 oxide by directly heating lead together with oxygen because lead forms compounds that are stable in the +2 oxidation state. So that means that for you to form lead 4 oxide, you need a special reaction, and that reaction is going to be for tri-lead tetraoxide, or which we call red lead. I'm emphasizing red lead because some of the times we say this question, we present it in that way. So red lead reacts with hot concentrated nitric acid, forming lead 4 oxide, and the other product is going to be lead 2 nitrate together with water, and this is the reaction for that. So warming a soluble lead 2 salt solution, such as lead 2 nitrate solution with sodium hypochlorite or chlorate 1 solution, can also yield us lead 4 oxide. So once you have a lead 2 salt, for example lead 2 nitrate, and you warm it with sodium hypochlorite or chlorate 1, in presence of water, you are going to be getting your lead 4 oxide together with your chloride ions and hydrogen ions, or preparation of an acid. The acid represents an hydrogen ion. So here you can have people who don't like the ionic equation, we can present it in terms of the standard equation. So you can write lead 2 nitrate reacting sodium hypochlorite in presence of water to form lead 4 oxide, sodium chloride, and nitric acid. Now you can have a sample question about that by saying, state and explain what would be observed when lead 2 ethanoate is warmed with sodium hypochlorite solution. So first of all, we shall see brown precipitate because lead 4 oxide is brown in color. You have to be very conscious about that, and you have to know their colors by simply reading your practical book. So we shall say brown precipitate, and the brown precipitate is due to formation of lead 4 oxide. So you're going to be saying that the hypochlorite ions in sodium hypochlorite solution are going to be oxidized. They are going to oxidize lead 2 ions in lead 2 ethanoate solution to form lead 4 oxide as a brown precipitate. And the hypochlorite ions, after oxidizing, they are going to be reduced to the chloride ions. And the equation is going to be the same as the one we wrote here. And I preferably urge you to write ionic equations, because when you write ionic equations, you can easily determine that the equation is balanced simply by looking at the charges. Now, looking at the dioxides, we start with the structures, just like we studied for monoxides, and these ones are the most commonly said. So structures of the dioxides of group 4 elements. So if you have carbon dioxide, it's having a covalent bond, and it's also it's having a structure of simple molecular or giant covalent structure. Now, carbon dioxide is having a simple molecular structure. Notice that there was an error in presenting this. Carbon dioxide is having a simple molecular structure. For silicon dioxide is the one which is having covalent bonding and is also having a giant covalent structure, together with germanium oxide, which has a covalent bonding and having a giant molecular structure. Now, tin oxide is having ionic bonding and having a giant ionic structure, together with the lead oxide, which is having ionic bonding and having giant ionic structure. So notice that when you're summarizing, tin oxide and lead oxide, they are both having giant ionic structures, and they are joined by ionic bonds, and the rest are joined by covalent bonds, but they differ in their structures, whereby carbon dioxide is having a simple molecular structure, silicon dioxide is having a giant covalent structure, and germanium oxide is having a giant molecular structure. Most of the times, these two, silicon dioxide and germanium oxide, they have the same structural configurations. So we are going to be looking at the properties of the dioxides of the group 4 elements, and we are going to start with carbon, and we are going to be stating why carbon reacts in specific ways. So first of all, carbon dioxide is acidic, and it reacts with water to form a weak acidic solution, and that is to say carbonic acid. However, this does not normally exist, so that's why we don't examine it. So carbon dioxide reacts with water to form carbonic acid, and then it also reacts with alkalis since it is acidic. The reason why it reacts with alkalis, now notice that carbon doesn't react with alkalis, but its compound, which is carbon dioxide, because it's acidic, reacts with alkalis, and when it does so, we form what we call a carbonate and water. So when you're having sodium hydroxide reacting with carbon dioxide, we form sodium carbonate together with water. And sometimes when used in excess, when carbon dioxide is present in excess, we form what we call sodium hydrogen carbonate. So silicon dioxide being acidic is also the reason why a reaction takes place between a base and a compound is because the other compound has to be acidic. So that's why I started by saying this one being acidic reacts with hot concentrated sodium hydroxide solution to form a complex, and that complex is always going to be sodium silicate and water. So when you react silicon dioxide together with an alkali, either sodium or potassium hydroxide being concentrated, notice that these alkalis have to be concentrated. We form a silicate or a sodium silicate or potassium silicate together with water. But ironically, that's going to be the equation. Now the dioxides of germanium, tin, and lead are amphoteric in nature. That means that they react with both bases and acids. So they react with acids to form corresponding salts and water. So they are going to be represented by general formula, or we can represent them by these equations. Now you're advised to avoid general formulas when you're answering your examinations and use these individual equations, because such general formulas are going to be reducing your marks. But rather, these general equations won't be doing that, and they may add you extra marks in case of the allowance to allow extra marks to a student who has presented them all. So germanium oxide reacts with an acid to form a germanium 4 salt. We are forming a plus 4 salt or a salt or an ion of germanium in the plus 4 oxidation state because we are using a compound which was in the plus 4 oxidation state. And the others are going to do the same. Lead 4 ions and tin 4 ions together with water. Now we are saying the lead 4 oxide Lead oxide oxidizes hot concentrated hydrochloric acid to chlorine, and itself is after oxidizing it gets reduced to lead to chloride and water. Now you looked at this under preparation of chlorine at O level, and you're repeating it here. So when you're having hot concentrated, not this word, it must be hot and concentrated. We're having two types of reactions of lead oxide together with hydrochloric acid. There's a reaction where hydrochloric acid is cold concentrated, and there's this reaction where it's hot concentrated. Now to bring out the aspect of being hot, when you're setting this question, we shall tell you that lead oxide is heated with concentrated hydrochloric acid. Once we say that heated, that means that we are using hot concentrated hydrochloric acid. So hot concentrated hydrochloric acid is oxidized by lead oxide to form lead to chloride, and after hot concentrated hydrochloric acid being oxidized, we form what we call chlorine gas. And then after lead oxidizing, it gets reduced to lead to chloride. We are saying it gets reduced because here lead is in the plus oxidation state, and the compound is forming, which is lead to chloride, is going to be in the plus oxidation state, and that's what we call reduction. Lead oxide oxidizes hydrochloric acid to chlorine gas and water, and itself is reduced to lead to chloride. So we complete by saying that lead oxide also reacts with cold. Now this term is cold or ice cold concentrated hydrochloric acid. That is to say, concentrated acid at 0 degrees Celsius to form lead chloride, which is a yellow liquid, and water. Now notice that here, all complexes, this complex that doesn't have the ion is going to be yellow. But when you're having concentrated acid reacted in excess with this yellow liquid turns to a colorless solution due to formation of a complex. The only complex ions that form colorless solutions are going to be those of transition elements. Here we don't have any group of element that forms a complex which is going to be colored. All their complex ions in solution are going to be colorless solutions. So when you use concentrated hydrochloric acid in excess, you form what you call a colorless solution. So from yellow liquid to a colorless solution, and the yellow liquid only forms because it's not a complex ion. So lead oxide reacts with cold concentrated hydrochloric acid to form lead chloride together with water. Now looking at further reactions, we are going to be looking at the dioxides of germanium, tin, and lead reacting with hot concentrated. I say that these elements react with only concentrated reagents. So reacting with hot concentrated sodium hydroxide solution to form, once they react with an hydroxide, which is concentrated, we always form complex ions. For monoxides, we are forming a germanate, but for these dioxides, we form a germanate 4, a stannate 4, and a plumbate 4, which can be either represented by this formula or we can use this formula. So you're going to be representing both alternatives on each and every equation. Now notice that during typing, versus steam typing, these arrows were displaced. So tin oxide reacts with the alkali to form this compound. Notice that the charge here is going to be 2 negative. It must be in this form together with water, or another alternative equation can be this. And lead will also form a plumbate 4, or the alternative equation can be this. For germanium, we form a germanate 4, and the alternative equation can be this. So these are the equations that will be required in case you are prompted to write or to describe reactions of group 4 elements or the dioxides of group 4 elements together with sodium hydroxide. Notice that sodium hydroxide must be hot and concentrated before you start describing those reactions. Now looking at the thermostability of the dioxides, you're going to be saying that the stability of the dioxides of group 4 elements is going to be decreasing from carbon dioxide to lead dioxide, and the reason for that is variation in stability, because the stability of the plus oxidation state decreases down the group. That's why the stability of the dioxides also decreases down the group. And we're going to be saying that the dioxides of carbon, silicon, germanium, and tin are going to be stable at very high temperatures. And also, but the dioxide of lead oxide, decomposes even at room temperature to form a more stable oxide, which is lead oxide, with liberation of oxygen gas. Now, such an explanation can be used to explain inert pair effect, whereby you talk about stability of the elements or stability of the oxidation states and what causes the oxidation state, together with giving an example of what is inert pair effect. Solid oxide, since plus oxidation state is very unstable down the group, it readily decomposes even at room temperature to form lead oxide or lead monoxide together with oxygen gas. Now we are saying that here, trilead tetroxide, which is also known as red lead, this is the most commonly used term, which is known as red lead, is a red powder prepared by heating lead oxide in dry oxygen, just like we said earlier on. So when you get a monoxide and you heat it with dry oxygen gas, you're going to get a trilead tetroxide, which is also known as red lead. We also say that it is a mixed oxide which represents lead oxide in some of its chemical properties as explained below. So we're going to be saying that both the oxides oxidize hot concentrated hydrochloric acid. Just like I told you, most of the reactions that are undergone by these compounds are with concentrated reagents. So always know that they do not react with most of the dilute reagents. They only react with reagents that are hot and concentrated, regardless whether it's an acid or it's an alkaline. So both of the oxides oxidize hot concentrated hydrochloric acid to chlorine, and themselves after oxidizing they get reduced to chloride and water. So lead oxide oxidizes hydrogen chloride to chlorine gas, and after oxidizing it gets reduced to chloride together with water. And the same thing to trilead tetroxide or red lead. It oxidizes hydrogen chloride gas or hydrogen or hot concentrated hydrochloric acid to chlorine gas, and after oxidizing it gets reduced to chloride together with water. So proceeding, we are going to be saying that both oxides are also going to be reacting with concentrated sulfuric acid to form sulfates, oxygen gas, and water. That means that sulfuric acid or concentrated sulfuric acid undergoes reaction with this lead oxide, and concentrated sulfuric acid oxidizes them or reduces them because it's from lead oxide to lead sulfate. So they are reduced by concentrated. Or now, since they are all oxidizing agents, the best term to use here is going to be they react. So we're going to be saying that lead oxide reacts with hot concentrated sulfuric acid, first of all to form a sulfate, which is in the plus oxidation state, together with water and oxygen gas. So that means that they're the ones oxidizing sulfuric acid, forming a little sulfate and water after oxidizing it, and also oxidizing sulfuric acid to oxygen gas. Trilate tetroxide also reacts in the same way to form little sulfate, water, and oxygen gas. And also both oxides are going to decompose on heating to form little oxide and oxygen gas. If you strongly heat them in a dry test tube, a brown solid is going to turn to a reddish brown solid, which is a reddish brown solid of little or lead monoxide, and oxygen gas is going to be evolved. So once you're heating a lead oxide, you're going to get a monoxide together with oxygen gas. And when you heat this red powder of trilate tetroxide or red lead, you're going to be getting lead monoxide or lead oxide together with oxygen gas. Now we are saying that lead oxide is an oxidizing agent. Together, lead oxide oxidizes the hot concentrated hydrochloric acid to chlorine and is reduced to little chloride and water, and we have looked at this reaction earlier on, and we said that it was used in O level in determining or in preparation of chlorine gas. Now looking at the observation, we shall be saying that this brown solid dissolves with the effervescence of a greenish yellow gas. Remember that the greenish yellow gas is due to chlorine being evolved, and also forming a colorless solution. Now the colorless solution is because little chloride is colorless in nature. Now, little chloride is supposed to be solid, but in concentrated or in hot concentrated acid, little chloride turns into aqueous. Little chloride is only solid when it is at room temperature. But if at all we are using conditions like hot or heating it with an acid, it dissolves on warming. Just like you do in your practicals, you will reach a part where they tell you to add silver chloride solution and warm. So that will be proven chloride. In case you get a white precipitate that is soluble on warming but precipitates on cooling, we confirm presence of chloride ions due to little chloride, or properties of little chloride. Little chloride is soluble on warming but insoluble on cooling. So it's a white precipitate on cooling, but on warming it becomes a colorless solution. Now looking at lead oxide, you are going to be saying that lead oxide oxidizes manganese to salts in aqueous solution in presence of concentrated nitric acid, forming manganese 7 ions. So this is a confirmation for presence of manganese 2 ions in the practicals, and it's highly examinable under theory, especially mock bodies. So lead oxide, which is a brown solid, oxidizes manganese oxide but in presence of an acid, forming manganese 7 ions. So we shall see a brown solid dissolving in the colorless solution to form what you call the purple solution, because manganese 7 ions make the solution purple. And then lead after oxidizing, it gets reduced to little ions together with water. Now the observation for that is going to be a purple solution being formed, because any compound containing manganese 7 ions forms a purple coloration. Also, lead oxide oxidizes sulfur dioxide to sulfur trioxide and itself is reduced to lead 2 oxide. So in having lead oxide reacting it with sulfur dioxide, you form what you call lead 2 oxide or lead monoxide and sulfur trioxide. And the lead 2 oxide and the sulfur trioxide then react together to give us what you call lead 2 sulfate. So the lead monoxide formed reacts together with the sulfate gas which is formed to give us lead 2 sulfate. So the general equation, in case you are being asked for it, because it's also examinable, but in case you are given 1.5 marks for that, you write the general equation that lead oxide reacts with sulfur dioxide gas to give us what you call lead 2 sulfate. Now the observation for that is going to be a brown solid, which is lead oxide, turning into a white solid, because lead 2 sulfate is a white solid. Now going to some explanations, we are going to explain why carbon dioxide is a gas at room temperature while silicon dioxide is a solid with a very high melting point. So starting with carbon dioxide, we are going to be saying that carbon is a very electronegative atom and has a very small atomic radius, and therefore it is capable of forming strong double bonds with oxygen, leading to formation of discrete molecules of carbon dioxide at room temperature that are joined, or that whose forces of attraction between them are weak van der Waals forces of attraction, and therefore is going to exist as a gas at room temperature. Because since these molecules are joined by weak van der Waals forces of attraction, you'll find that molecules are going to be sparsely present in matter. So being sparsely present in matter, it makes it exist in gaseous state. But the main reason for that is due to its small atomic radius and also it being very electronegative atom among all the other atoms of the group 4 elements. So looking at silicon, you are going to be saying that silicon has lower electronegativity and also it has a larger atomic radius, hence cannot form multiple bonds with oxygen, but it forms single silicon-oxygen bonds with each silicon atom bonded to 4 oxygen atoms. And if each silicon atom is going to be bonded to 4 oxygen atoms, we form what we call a three-dimensional giant covalent structure. And such structures are strong, and therefore silicon dioxide exists as a solid with a very high melting point. So notice that each silicon atom is bonded to 4 other oxygen atoms. That means that it forms a tetrahedral shape, just like carbon in carbon tetrachloride. So being in this shape, it forms what we call a three-dimensional structure. And the three-dimensional giant covalent structure is very strong at room temperature in such a way that will enable silicon dioxide to exist as, or the oxide of silicon or silicon dioxide to exist as a solid at room temperature. The reason why carbon dioxide exists as a gas is because it has a small atomic radius and is highly electronegative. And together, it forms strong double bonds with oxygen that exist as discrete molecules joined by weak van der Waals forces of attraction. And since the forces of attraction between its molecules are weak, it exists as a gas at room temperature, unlike silicon dioxide. So let's look at the dichlorides or the chlorides that are present in group 4 elements. So we're going to be saying the elements form 2 types of chlorides. We have what we call the tetrachlorides that are present in the +4 oxidation state. We also have what we call the dichlorides that are present in the +2 oxidation states. So you're going to be starting with the preparations, and you're going to see that carbon tetrachloride is prepared by simply passing chlorine gas through carbon disulfide. So when you're having carbon disulfide, which is a liquid, you react it with chlorine gas, which is dry, you've prepared what you call carbon tetrachloride. Now notice that you cannot prepare carbon tetrachloride by heating carbon directly with chlorine. That reaction is not feasible. We only prepare it with special or very unstable reagents like carbon disulfide, reacting it with an oxidizing gas such as chlorine to form the stable compound, which is very inert and being used in organic chemistry, which is carbon tetrachloride. And also, together with carbon tetrachloride, we also form disulfide dichloride as another compound. So the other tetrachlorides, except that of lead, can be prepared by directly heating the element with dry chlorine gas. So when you have heated silicon together with dry chlorine gas, we form what we call silicon tetrachlorides. And all the tetrachlorides, notice that they are going to be covalent and they are going to be joined by simple molecular structures and they exist in liquid states. All the tetrachlorides of group 4 elements are going to be in liquid states. So silicon reacts directly with chlorine to form silicon tetrachloride, which is a liquid, and germanium reacts with chlorine directly when heated to form germanium tetrachloride, which is also a liquid. Together with tin reacts with chlorine to form what we call tin 4 chloride, which is also a liquid. They all have simple molecular structures and they exist as liquids. And it's so that when something is having a simple molecular structure, they are explained in terms of van der Waals forces. So when you ask a question about melting or boiling points, notice that you are going to be in that line. So going to lead 4 chloride, we are going to say that lead 4 chloride is going to be prepared by reacting lead 4 oxide together with cold. Notice that this word here, we have already looked at this reaction. For us to prepare lead 4 chloride, we need cold concentrated hydrochloric acid. The condition here is cold. If it is hot, we get chlorine gas. It's an oxidizing reaction. But if it's cold, it's not an oxidizing reaction. What it does at 0 degrees Celsius, we get lead oxide and react it with cold concentrated hydrochloric acid to get the tetrachloride of lead. And all tetrachlorides, like I've told you that there must be in liquid state together with water. However, if the acid is added in excess to this lead chloride, the chloride ions present in excess react with the lead chloride or lead tetrachloride to form a complex, which is going to be hexachloropyrambate 4 complex, which is also, now this complex is not yellow, it's a colorless solution. So we say that a colorless solution is formed because the only elements that form colored complexes are transition elements. The other ones, for as long as it's in aqueous, we form what we call colorless solutions. So lead chloride, which is aqueous, reacts with the excess chloride ions present in the solution to give us a complex, which is called hexachloropyrambate 4 complex ion. So that's it about reaction of lead chloride with cold concentrated hydrochloric acid in excess. So first of all, if it's present in limited amounts, we form lead chloride. If the acid is in excess or is added in excess, extra chloride ions react with that compound you have formed to form hexachloropyrambate 4 complex. Now furthermore, looking at the thermostability of the tetrachlorides, we are going to be saying that like I told you, all those ones are covalent compounds. So that means that they are going to be joined by weak bonds. But whenever you are talking about thermostability, the only emphasis you should focus on is going to be bond length. That's the only focus you should put your attention to. Whenever you're talking about thermostability, we only focus at bond length. Bond length, you explain in terms of bond length. So we're going to be saying that thermostability is going to be decreasing down the group. And the explanation for that is going to be the atomic radius of group 4 elements increases down the group, and that is from carbon to lead. And therefore, covalent bonds between the group 4 atom and the chlorine becomes longer. And the longer it becomes, the weaker it gets down the group. And therefore, the amount of energy required to break those covalent bonds in those tetrachlorides is going to be decreasing progressively down the group. Hence, a decrease in thermostability from carbon to lead tetrachlorides. This is going to mean that carbon tetrachloride, silicon tetrachloride, germanium tetrachloride are stable even at high temperatures, but tin chloride and lead chloride are going to be decomposing readily even on slight heating. And you're going to be saying that lead tetrachloride and tin tetrachloride decomposes even at room temperature. But most of the time it's going to be lead tetrachloride, which it decomposes at room temperature to form the most stable chlorides, which is going to be dichloride and chlorine gas. Just like I said, carbon tetrachloride is going to be very stable, so it's going to decompose together with the other chlorides, the other 3 chlorides. But tin chloride and lead chloride, for them they already decompose. This one requires slight heating to form tin chloride with the chlorine gas. But for lead chloride, decomposes readily at room temperature to form a dichloride together with chlorine gas. So we shall see effervescence of a greenish yellow gas. But I've told you, whenever you're explaining anything in some thermostability, anywhere in inorganic chemistry, you have to explain in terms of bond length. That means that you have to include the atomic radius, the atomic size, and what is happening progressively down the group. And after talking about the atomic radius, you talk about the bond length. After talking about the bond length, you talk about the bond strength. The longer it is, the weaker it is. The shorter it is, the stronger it is. So let's look at the hydrolysis of the tetrachlorides. Just like I said, whenever you hydrolyze any chloride, you form what you call fumes of hydrogen chloride gas. Now, if they are in +4 oxidation state, we form +4 oxides. So let's look at it. If you're having silicon tetrachloride and you hydrolyze this in water, you form white fumes of hydrogen chloride gas, and then you form silicon oxide. We are forming silicon oxide because our compound was in the +4 oxidation state. Or the other alternative reactions for that can be this, but for as long as you're having hydrogen chloride included in your reaction. But the best reaction is going to be the first one. So germanium tetrachloride hydrolyzes in water to give us germanium oxide and hydrogen chloride gas. Same applies to tin chloride, which gives us tin oxide and hydrogen chloride gas. Alternative equation can be this. Same applies to lead for chloride. I've told you can pick the first equations to be your best equations where possible. Usually don't go with these ones due to the errors they have, or they may be uncommon among a lot of textbooks. So this one gives us lead oxide, which is a brown solid together with white fumes of hydrogen chloride gas. Now we are saying that the tetrachlorides of silicon, germanium, tin, and lead are hydrized because these elements have empty or vacant d orbitals, which accommodate lone pairs of electrons from ligands such as water molecules. However, carbon tetrachloride, just like we talk about it in inorganic chemistry, carbon tetrachloride is not hydrized because if you look at its electronic configuration, it lacks vacant or empty d orbitals. So it lacks vacant or empty d orbitals to accommodate lone pairs of electrons that are coming from water for such a reaction to take place. So let's note that because it's very, very important. We shall tell you why does silicon tetrachloride undergo hydrolysis whereas carbon tetrachloride doesn't. So you say that silicon atom in silicon tetrachloride has vacant d orbitals that accommodate lone pairs of electrons from water molecules. But carbon in carbon tetrachloride lacks vacant d orbitals to accommodate lone pairs of electrons from water molecules. Therefore, carbon tetrachloride cannot undergo hydrolysis reactions. That's the best way of answering such a question. Now going to dichlorides or the dichlorides, which are in this form, we are going to be looking at the preparation of the dichlorides, and we are going to be saying that germanium 2 chloride is going to be made by passing vapor germanium 4 chloride over heated germanium itself. Remember that these elements, just like we are preparing monoxides from dioxides, these elements are reducing agents to their compounds themselves. So when you have germanium tetrachloride, you heat it germanium solid. You heat, you are going to form a germanium 2 chloride or a germanium dichloride, which is present in solid state. Now here we are also going to be saying that anhydrous tin 2 chloride is best obtained by heating tin in a current of dry hydrogen chloride gas. So if you're having tin, you heat it with hydrogen chloride gas, you're going to form tin 2 chloride together with hydrogen gas. When you're having tin, you heat it with hydrogen chloride gas, you're going to form tin 2 chloride together with hydrogen gas. And you're saying that hydrated tin 2 chloride can be obtained by heating tin, first of all with hot concentrated hydrochloric acid, or simply reacting tin oxide with dilute hydrochloric acid followed by crystallization. So there are two equations. First of all, you get tin and react it with hot concentrated hydrochloric acid. You're going to form tin 2 chloride together with hydrogen gas. Or you can get an oxide, react it with hydrochloric acid, which is dilute to get into chloride and water. Now we are saying that here, little chloride is prepared by simply precipitating dilute hydrochloric acid together with sodium chloride together with aqueous solution containing little ions. For example, little nitrates and also little ethanoids. Both of them contain little ions. So little ions react with the chloride ions to form what we call little chloride. Now looking at the hydrolysis of the dichlorides, if you hydrolyze germanium 2 chloride, you are going to get germanium monoxide together with hydrogen chloride gas, and germanium 2 chloride is covalent and is therefore hydrolyzed by water, forming a monoxide and hydrogen chloride gas. And the observation that you'll be seeing there, you're going to be seeing a yellow solid, which is going to be that of germanium 2 chloride, to turn to white solid because all oxides are going to be white, and white fumes are going to be formed. Now looking at the anhydrous tin 2 chloride, anhydrous tin 2 chloride is predominantly covalent and therefore is going to react with water, but for it, it's going to form what we call a white suspension of basic tin 2 chloride with liberation of white fumes of hydrogen chloride. For tin, when tin 2 chloride, this is a very common question. When tin 2 chloride reacts with water, we form what we call a suspension, a white suspension, and that white suspension is going to be basic tin 2 chloride, which you write in this format, and it's going to be a solid together with fumes of hydrogen chloride gas, because we say that whenever you're hydrolyzing a chloride, you must get hydrogen chloride fumes, which are white fumes. So we're also going to say that if water is hot and present in large excess, which is rarely present or rarely the case, we can get what we call tin 2 chloride to form, and tin 2 hydroxide and hydrogen chloride. So tin 2 chloride reacting with water in such a case is going to give us tin 2 hydroxide together with hydrogen chloride gas. Now let's look at the other compounds that are going to be hydrides of group 4 elements. And here we are going to be saying that here the elements from tetravalent hydrides, that is to say methane, selene, german, stannate, and plumbane, they are going to be formed in that way. So hydride of silicon is called silane, and hydride of carbon is going to be called methane, just like you look at it in organic chemistry. Hydride of germanium is going to be called germane. That of tin is going to be called stannine, and that of lead is going to be called plumbing. So whenever you see such terms, we are referring you to hydrates. Now we are saying that all these hydrates are going to be covalent and colorless gases at room temperature. That means that they are held by simple molecular structures. And anything that is held by simple molecular structures, that means that whenever you're explaining melting points, you talk about the structure, the forces holding such structures are always called weak van der Waals forces of attraction, which depend on molecular mass or molecular size of a given compound or an element. Now we are saying that here, the boiling points increase from methane to plumbing simply because they have, first of all, they have simple molecular structures. And the other thing is due to increase in atomic radius from carbon to silicon to germanium. And in such a case, it's going to increase the molecular mass from methane to plumbing, and therefore the van der Waals forces of attraction between their molecules is going to be increasing progressively down the group from the hydride of carbon to the hydride of lead, causing a strength in the same direction. Just like the way you explain things that are held by weak or that have simple molecular structures. You talk about the structure, which is simple molecular structure. You talk about how it is, what forces holding it, which is van der Waals forces, and then you talk about what they depend on. They depend on molecular size, but molecular size in turn depends on increase in atomic radius. The larger the atomic radius, the larger the molecular size. And the larger the molecular size, that means that the stronger the van der Waals forces get. That's why the boiling points or the melting points of such hydrates are going to be increasing down the group. Now looking at the preparations of such hydrates, we are going to be saying that methane is prepared by hydrolysis of beryllium carbide or aluminium carbide or heating sodium ethanoate with soda lime. Soda lime, remember that in organic chemistry, it's a mixture of sodium hydroxide together with calcium oxide, but both of them must be solids. So when you have beryllium carbide and aluminium carbide, and I'm well aware that you looked at these ones under diagonal relationships. So beryllium carbide and aluminium carbide hydrolyze in water to give us hydroxides. Now since both of them are phosphoric, the hydroxides must be solid in nature. And then after hydrolyzing, they give us what we call methane gas. So that's how we prepare the hydrate for carbon. Or you can simply react sodium ethanoate with sodium hydroxide, forming methane gas and sodium carbonate. It can also yield us the hydrate of carbon as well. Now you can see that the hydrates of silicon, germanium, tin, and lead can be made by reduction of their tetrachlorides with lithium aluminium hydrate, but this must be at 0 degrees Celsius in presence of ether. Whenever you're using lithium aluminium hydrate, you make sure that it's in presence of ether as a condition, and also the temperature must strictly be 0 degrees Celsius. So silicon tetrachloride reacting with the lithium aluminium hydrate, we form what we call silane. Silane is the hydrate of silicon. Lithium chloride, lithium and chloride, and also aluminium chloride. For that of germanium, we form germane, and for that of tin, we form stannine. For that of lead, we form what we call plumbing, together with lithium chloride and aluminium chloride, and they are going to be represented by such equations. We can also say that silane can also be prepared by simply reacting magnesium silicate with dilute hydrochloric acid. So if you're having magnesium silicate, you react it with dilute hydrochloric acid, you're going to form silane together with magnesium chloride. Now looking at the thermostability of the tetrahydrides, just like I've just mentioned, when you're explaining any concept about thermostability, you talk about bond length. You focus about bond length specifically. So you're going to be saying that when heated, they all decompose to form the element and hydrogen gas, and the ease of decomposition or the ease to decompose increases down the group due to decrease in the decomposition temperature shown in the table below. So these ones are going to be their decomposition temperatures or their thermostabilities at varying temperatures. And you're going to be saying that thermostability of these hydrates is going to be decreasing down the group. And the reason for that is because atomic radius is increasing. Once atomic radius is increasing, that means that covalent bonds between the atoms is becoming longer. And the longer the bond length, the weaker they become. resulting in 2, a decrease in the decomposition temperature, hence a decrease or hence a progressive decrease in the thermostability 2 or correspondingly. Now this brings us to the end of this video. You are advised to subscribe to the channel, like the video and share it to friends. We'll meet in the next video handling another group for elements. For those of you having papers, to make excellent success in your papers.